Well, good morning, everybody. So just a couple of scheduling matters before we start. So according to the Guelph schedule, which I guess we're a week behind the Waterloo schedule, but the final week of the semester in Guelph is going to be the week of April 4th. So on April 4th, that's the Wednesday, we would have officially the last two lectures for this course. I say officially because, well, depending on how things are going, I may wish to extend the lectures by one or two on April 11th. So I'll decide pretty much on the spot on the 4th, to see what I managed to cover, and if I need a little bit more time to cover all I wanted to cover, I'll invite you to come again on April 11th. Sorry, this was supposed to be April 18th. So the presentations from all of you will occur on the 18th. So by now you should have been well on your way to do the research for your term project and get the ball rolling on this. But you have until the 18th to prepare a presentation, 20-minute presentation, and the term paper that comes with it. So I'll be collecting the term papers on that day, and I'll be listening, and we'll all be listening to your presentations that day. So we'll have a session in the morning, and if we need one, we'll have a session in the afternoon, pretty much keeping the same schedule. But I think that can be flexible. We can work on that a little bit later. And yeah, so the point is that while you need to prepare something to present to the rest of us, I'll give you 20 minutes. And in those 20 minutes, well, you have to tell us the story of what you've learned during your term project. And, and then you have to choose, how you're going to present this. You're going to have to, decide to, so I don't want, lots of details necessarily, but I want enough to convey, the essence of what you've learned. So choosing what you're going to do in terms of presentation, I think is, a pretty important aspect of preparing the presentation itself. So, the planning of the presentation is probably as important as the presentation itself. So that's something you can think about before you come to that day. But that should be a fun day. So we'll all learn from each other. So I'm looking forward to that. And but anyway, so now you have your official deadline to work with. So any questions about that? Okay. So let's go back to where we were last week. So last week we did a lot of work. The last 2 weeks were pretty heavy. At the end of the lecture on last Wednesday, I finally gave you the form of the gravitational action written in the 3+1 decomposition, something that is the starting point for constructing a Hamiltonian. So after doing a lot of work, we ended up with an expression for the gravitational Hamiltonian, for the gravitational action, that was expressed as a time integral of something that involves an integration over a hypersurface sigma t, and we have a whole stack of them, as you remember. So we have the bulk term in the action that involves the 3 curvature on each hypersurface, the square of the extrinsic curvature in this combination, and that we integrate over each hypersurface, and that we integrate over time. So that's d3y. So that's the bulk part of the action. And we also have a boundary term on each sigma t, and that involves the lapse. It involves the difference between the two-dimensional extrinsic curvature on st embedded in sigma t, and something that, while I talked only briefly about last time, that needs to be regularized with a subtraction term the same way that we did it in the case of the original form of the action. So I dropped this for the calculation last time, but I've just reinsert it now because, well, it achieves exactly the same purpose. So it regularizes the action in the same way that the original k-naught term did before, and this we integrate over the full boundary. So that's the surface term, the boundary term. That was the bulk term, and the picture behind this is that, well, we have a 4-dimensional volume of space-time that's foliated in terms of sigma t hypersurfaces. So this is sigma t. The boundary of sigma t is st. And we integrate from t equals t1 to t equals t2. And then, well, the notation, I think, is pretty explicit. So KAB is the 3D extrinsic curvature of sigma t embedded in space-time. K, well, I'll put the indices on it, would be the two-dimensional extrinsic curvature of st embedded in sigma t. And K naught would be the two-dimensional extrinsic curvature of st embedded in flat space. And again, the purpose of inserting K naught, which I dropped in the lectures last week, is to regularize the action in the sense of giving it a well-defined value if you choose to extend the boundary all the way to infinity. So it's the same issue that we discussed at the level of the original form for the gravitational action. And other than that, well, we have, the induced metric on sigma t, we have the induced metric on st, we have the lapse function, and at this stage, the shift vector doesn't make an appearance, but the shift vector will come back, very soon, and in fact, it will be involved in the definition of the canonical momentum associated with the metric. So, any questions before I get going with this? All right. So, that's the action written in a suitable form for a Hamiltonian, calculation. And the first step in the Hamiltonian calculation is to define the canonical momentum associated with the metric, and then calculate it, and then do the usual inversion between the Lagrangian density and the Hamiltonian density. So the canonical quantity here, the canonical field that we're dealing with is going to be the three-dimensional metric. So after the 3+1 decomposition, what emerges from that is that the dynamical quantity that describes the gravitational field here is no longer the full four-dimensional metric. The full four-dimensional metric was decomposed into a three-dimensional metric on each sigma t. That's going to be our main dynamical variable. And we have a lapse and a shift. But the lapse and the shift are not going to be considered to be dynamical variables in the same light, for a reason that will become very clear in just a second. So basically, so we can decompose the full metric into a 3D metric, a lapse, and a shift. That's what we did last time with the 3+1 decomposition. But only the induced metric, only the 3D metric, can be considered to be a dynamical variable. The other ones are just playing the role of Lagrange multipliers, essentially. They are providing the freedom of specifying the coordinates in space-time, but the 3 metric is a real canonical variable, one of the two main canonical variables. The reason for this is that, when you're given an action, the way to spot what the canonical variables are going to be is that, while you pick the terms in the action that depend on the time derivatives of your proper dynamical variables, of your proper dynamical degrees of freedom. And what we'll notice in just a second, or what we can recognize right away, is that when we stare at the action right here, we notice that the action depends on the extrinsic curvature. It depends also on the three curvature, but most important for us here, it depends on the extrinsic curvature. And we know that in a precise sense, the extrinsic curvature is something that represents the time derivative of the metric. So we see here that the action, will depend on h through, the 3 curvature, and also, the integration measure. So there's a dependence on h, but there's also a dependence on h dot, which is hidden within k. So that we know will give us, a canonical momentum for the metric, this dependence on h dot. But when we stare at the metric, at the action, we see a dependence on n, but we don't see a dependence on n dot. There's no n dot to be seen, there's no n dot to be found in the action, and that guarantees that there will be no momentum associated with n. And that means that n is not, is not really a dynamical, part of, it's not a part of the dynamical degrees of freedom. It's something that really plays the role of a Legendre multiplier, and basically we don't have a canonical pair of variables associated with n. And the same is true for the shift. So the shift will occur in the next set of manipulations, but we'll see a dependence on the shift coming out, but we won't see a dependence on the time derivative of the shift. And again, that tells us that the shift vector is not part of the true dynamical degrees of freedom. N and A basically are there to specify the coordinate system in space-time, given the three-dimensional coordinate system on each hypersurface. And that specification is completely arbitrary. So it's sort of natural, it's sort of to be expected that n and the shift vector, that the lapse in the shift vector will not be part of the true, listing of, dynamical degrees of freedom. So bottom line is that we'll be searching for canonical momentum for the induced metric, the three-dimensional metric, but we won't be looking for canonical momenta for n or the shift vector. Okay, so having said this, let's do the work now. So when we did this with the scalar field theory, we never had to worry about a boundary term. And what we defined the canonical momentum to be is basically the derivative of the bulk Lagrangian with respect to, well, the Lagrangian, which in the scalar field case was just the bulk Lagrangian with respect to the time derivative of the field. So here we have the boundary term, but the boundary term really doesn't play a role in the extraction of the momentum, because the boundary term doesn't involve big K, it involves only small k, and small k is quite independent of the induced metric. So, well, it's not independent of the induced metric, it's independent of its time derivative. So the only appearance of a time derivative of the induced metric occurs through big K. So bottom line is that, well, this part of the action doesn't contain an h dot in it, and therefore will not participate in the calculation of the canonical momentum. So all we have to worry about to calculate the canonical momentum is the bulk part of the action. So in that sense, the boundary term doesn't complicate the picture too much, and basically it will just come along for the ride. It's not going to be something that interferes with the extraction of the canonical momentum. Okay, the first thing I have to do here to extract the canonical momentum is to define what we mean by h dot, right? And in the scalar field theory there was no distinction between partial derivatives and covariant derivatives and Lie derivatives, but I made it clear at that point that the proper interpretation of a dot here will be through a Lie derivative along the flow lines that we were given. When we were constructing the 3+1 decomposition, there was a vector T alpha that was tangent to flow lines, and what we're doing here is to take a Lie derivative with respect to that flow. So we have a vector T alpha with respect to which we take partial derivatives, and what we're supposed to do here is to, what we're doing here is to define h dot to be those Lie derivatives, which means that we're taking the Lie derivative of the induced metric, and because the basis vectors are Lie transported, have a vanishing Lie derivative with T alpha, what that means is that all we need to do is to take a Lie derivative of the metric itself with respect to the vector T alpha, and when we evaluate the Lie derivative, that means that we take the symmetric combination of covariant derivatives of the vector T alpha. So that is what we mean by h dot. And the next step is to just go ahead and compute this. So T alpha, we remember, is given by the lapse multiplying the normal vector to each hypersurface plus the shift vector multiplying the tangent vectors to each surface. So just to save notation, I'll call this n alpha. So I'm promoting here my three-dimensional vector into a four-dimensional vector by involving the projection to the hypersurface. So that's a push-forward operation. So if I want to take a covariant derivative of this, well, first I take a covariant derivative of the lapse function. Then I take a covariant derivative of the normal vector. And then I take a covariant derivative of the shift vector in its four-dimensional form. Now, I'm taking partial derivatives only in the tangential direction. So let me just do this, projection now. So after projection, I get no contribution from here because the normal obviously is going to be orthogonal to the tangential vector, so I get no contributions here. And from this term, I get something that we recognize as being the definition for the extrinsic curvature. And for this guy, I get something that I recognize to be the intrinsic covariant derivative of the vector within the hypersurface. So that combination here ends up giving me n times KAB plus NA/B. And that's basically the intrinsic covariant derivative that's defined relative to the induced metric on each hypersurface. So that's just, I mean, that's something I talked about last time, that this projected covariant derivative is, is a definition for what we would mean by the intrinsic covariant derivative of the vector within the hypersurface. So bottom line, I symmetrize this, and I get that H dot AB is going to be 2n KAB because KAB is already symmetric. And then I get NA/B plus NB/A. And that's what stands for H dot. And we see, as I said, that, well, most of H dot is provided by KAB, but the shift vector now has made its appearance, and the shift vector is also involved in this expression for H dot. So there's a time evolution because you move normal to the hypersurface, but you're really moving with the flow. So you move with the you move normal to the hypersurface. That's this term over here, and you move, tangentially to the hypersurface as you follow the flow, and that's this contribution over here. All right. So that's what we mean by H dot, and what I would have to do here in principle is to go back to my action and replace each occurrence of KAB with an occurrence of H dot. And then we're going to go back then to that action and calculate partial derivatives with respect to H dot to get the momentum. So that's the operations that we're supposed to go through now to get the momentum out of this. All right, any questions? Are you guys happy? Yeah, okay. All right, so let me keep this there. Let me keep this here. So now we want to get the momentum out of all this. So the momentum, I'll call it PAB, according to the standard definition that we would get for any field theory. The momentum will be a derivative with respect to H dot of, square root minus g times the Lagrangian density. So that would be a definition, but here we've agreed that only the bulk term will contribute to that. So I don't have to worry about keeping the boundary term here. Only the bulk term will contribute an H dot, that will contribute to the momentum. There's no occurrence of the shift vector inside the action. So what I can do, instead of taking derivatives with respect to h dot, I can, apart from this vector of 2n, I can take derivatives with respect to KAB directly. And that will be a little bit simpler. I don't have to do the substitution that I talked about. So it will streamline the calculation a little bit. So instead of calculating these partial derivatives, I can just divide by 1 over 2n and take a partial derivative with respect to KAB. And of course, what appears inside the bulk action, square root minus g, will stand for n times h under the square root. And then the rest of it is 3r plus, here I'll have to be careful with my indices, so let me call this kcd minus k squared. And that's it. So that's my bulk action. The n's nicely go away. The square root of h will just come along for the ride. And the 3r here will be inert here. It doesn't do anything. It will not contribute. So the only terms that I need to worry about here are those. So that's a pretty simple calculation. So let me just rewrite this. So I get the 1/2. I get the square root of h. I get d dkab. And what I'm going to do is to rewrite this in a way that's going to make it easier to calculate those partial derivatives. Because here we have, a bunch of KABs, but we've involved the metric in constructing those contractions here. So I just want to make all of this explicit so that we can take the partial derivatives, easily. So what do we have? Right. So this I'll write as, so inside the bracket here, I'll just ignore 3r because it doesn't contribute. So we get kcd, sorry, I need the indices. I need the indices down here. I'll write it as kcd, kef. And this will multiply, KCD is right here, but to get a KEF, to get a KCD from a KEF, I need to involve the metric. So it's going to be metric HCE and then HDF. And then after multiplication here, I've raised all the indices and I get the first term. And then to get this contribution here, I need to involve the metric to convert each of those into a trace term. So here I have HCD multiplying HEF. Right? So that's just this written in more explicit notation. And the reason for doing this now is that, looking at this, I can now take partial derivatives more easily. And evaluating that, I apply the product rule. And it's the usual game where, if I want a non-zero contribution here, I have to have, when I differentiate this guy, I have to have A agreeing with C and B agreeing with D. Otherwise, I get 0. And it's the same story when I differentiate the next guy. So when I differentiate KCD, I'll get AC with the delta and a delta BD. And this will multiply KEF. And I'll get another contribution where KCD is left alone. And here I need agreement between A and E and B and F. So that's the outcome of taking partial derivatives. Yep.
Should you have another term? Because in this case, the metric, A and D are the same, B and C are the same. That should still be non-zero, right?
Yeah. So in principle, what I should do is to symmetrize.
Okay.
Here and here. And you're right. So if I were to look at this in isolation, I would absolutely need to do that. What saves me here, the reason why it's not really, while it wasn't really necessary to do it here, is because this symmetrization becomes redundant because I'm multiplying by something that has that symmetry property. So it's better to do it. because it's actually, the correct result. But, sometimes you can take a shortcut when you know that the symmetrization operation is going to be taken care of when you do the rest of the calculation. But thank you for pointing this out.
Should you get a factor of 2 then?
That's implicit in the bracket. So when you symmetrize, you multiply by a half. So the bracket notation includes that 1/2.
Shouldn't you get a full term of each?
Yes, I think so. But I don't want to say so. I don't want to say yes because I know it'll produce a wrong factor. I think I want to contradict my previous answer. I think the rules of partial differentiation when you're dealing with tensors don't recognize symmetric tensors. They don't account for that. So basically, you have to treat each component as being independent. That's what a partial differentiation would mean. So you differentiate with respect to H01, understanding that this is in principle independent from H10, or K in this case. So so the rule of partial differentiation is that you really treat each tensorial component independent, even though the tensor itself might be symmetric. So in fact, we should not symmetrize even if we were be tempted to do it. And basically, and that's something I should have reflected on before today, but I think that's just inherent to the rules of partial differentiation. That's what partial differentiation means. You differentiate with respect to one thing, keep all the other guys fixed, and momentarily you have to suspend the knowledge that you have that this tensor might be symmetric or antisymmetric. I know it's not totally satisfactory. It seems a bit strange, but if I want this to work, I have to declare that. All right. Okay, so now we can just undo the algebra here. So we still have our 1/2 times h, and this will multiply. So now we're going to have a big mess of terms. So we're going to multiply KEF by all of this, and now I'm going to do the contraction. So C is being replaced by A, and D is being replaced by B, so we get HAE times HD, sorry, D is being replaced by B, so it's BF, minus HAB times HEF. So that's the first term, and then the second term we have KCD. That's being, and then we replace E by A and F by B, so we get ACA HDB minus HCD HAB. And if you look at this, unless I made a mistake, when you look at this, I think you see that we have twice the same contribution. We just relabeled the dummy indices here, and we get exactly twice the same set of terms. So in the end, we get that our momentum, I can kill the 1/2, and that's why I didn't want an extra factor of 2 here, because I know that this is the correct expression. So so the canonical momentum is going to be a factor of root h, and then it's going to be k Okay, I'm sorry. I put the indices in the wrong place. Those are upper indices because those are lower indices that occur in the denominator. So those again are upper indices. And what we get is KAB minus K multiplying HAB. And that's our canonical momentum associated with the three-dimensional metric. And it's pretty much what we would expect. Roughly speaking, we know that the canonical momentum is something that stands, apart from factors, it stands for the time derivative. It stands for the velocity field associated with your field, and that's being represented by h dot, which is being represented by k. So in the end, we should have expected the relationship between P, A, B, and k. The factor of h here is inherited because there was this factor of root g inside the definition, and the shift vectors disappeared because it's not involved in the action itself, in the action. So in the end, we just end up with this proportionality between the canonical momentum and the extrinsic curvature. The only thing that's not obvious is that it occurs in that combination, right, where we subtract a trace term from KAB. But other than that, I think the relationships are sort of plausible. Questions?
Can you quickly remind me why we chose to differentiate with respect to the Lagrangian density, including the root g, as opposed to just the Lagrangian?
Yeah, so that's something that I talked about last week when we were doing this, in case of the scalar field theory. Mm-hmm. So it appears to be a fact of life that when you go from the action to the Hamiltonian, you go away from describing. So you go away from scalars, and you do this in terms of scalar densities, which are almost scalars except for that factor of root g. So the Lagrangian density includes that square root. So the Lagrangian density, we'll come to that in a second, is going to be PAB H dot AB minus root GL. So the Hamiltonian density includes that root g, but the full Hamiltonian for the system then is just a straight integral without a root g in it or without a root h in it. So all of those, so you accept the fact that this is going to be a scalar density, but you integrate it straightforwardly so that in the end you end up with something which is,
is that
not quite a scalar, but in any case,
Is that just like the choice we make? I mean, if we didn't include the root g, but we included the root g
at this level, yeah.
Would that be okay as well?
I tried that. That would have been my favorite approach. So when I was working through all of this stuff, in the earlier incantations of this course, I was really trying desperately to do it like this, and in the end, I ended up with a failure. And right now, I no longer remember what the reason was for this, what broke down. But I think in the end, it ended up being so non-standard that it would have been basically a departure from what has been traditional in this game. And what people have done since they got started in this game is to define the Hamiltonian density as a scalar density, not a scalar. And they absorb the root g. And that's why you have leftovers of root something in all the quantities. Whether there's something fundamental there or something that's just accidental, by historical tradition, I really don't know. I never really got to the bottom of this. But let's just accept it as the traditional way of doing things. And I'm not going to topple tradition. There might be consequences. Okay. Other questions? Okay, so that's the canonical momentum associated with our induced metric. And while the rest of the construction is basically just doing what I did here, we're gonna build the Hamiltonian by doing the this usual inversion. And we have all the elements in place now. We have h dot from here, we have p from here, we can put it all together and go back to the original action to get the rest of it, and that will give us our Hamiltonian. In principle, what I should be doing is to express the Hamiltonian in terms of p and h. You know, the Hamiltonian is always supposed to be expressed in terms of the canonical variables. What I'm going to be doing, though, is to keep on expressing it in terms of k and h. So k will act as a stand-in for p. I can easily invert this relation by taking the trace and subtracting. So if we know p, we can get k. If we know k, we can get p. So for me, k is just a little bit more convenient because the equations will look a little bit more recognizable if we keep expressing the Hamiltonian in terms of k instead of p. That's a small matter, but you know, in principle, we really should be expressing everything in terms of p, not k. But that's a place where I'm going to take liberty and not do that. All right, so let's just do it. So h is given over here. So PAB is given right here, so we have h KAB minus KHAB. H dot is given over here, so we have 2n KAB plus NA slash B plus NB slash A. So that's this part of it, and then we subtract the bulk Lagrangian first. So the bulk Lagrangian is given up there, and it includes that factor of root g if I yeah, so the factor of root g is already included here, so I don't have to, no, sorry. Yeah, I'm wondering if I need to insert a factor of n or not. Because I know that root g is n times root h. I already have the root h. Should I insert the root n? No, well, according to my notes, that's the correct expression. Oh, no, you're right. There was a factor of n missing. That makes more sense. Sorry about that. There was an n missing here, and now I have my full root g, which was a problem before. So, yeah, so I had it there, and then here I don't care. Over here I cared, but I had it right. I had it right here. So the n that I was missing previously was reinserted here, so I was fine here. So sorry about that. I was just missing an n in the expression for the action because my notes were wrong. Okay, so now I'm happier. So we have n that multiplies the 3 curvature plus KAB minus k squared, and that multiplies root h. And, but we also have to subtract the bulk term now. So now the bulk term comes and appears inside the Hamiltonian. So it comes with a minus sign this time, and we have the bulk term. And inside the integral, we have another n. We have a k minus k naught. And we have a root sigma d2 theta. So now all we have to do is to clean this up a bit. So I will collect all the terms that involve an n and a root h. So first we get 2 KAB, KAB. And we get minus 2 k squared because I get my 2, I get my k, and I get another k by multiplying KAB with HAB. Yep.
So I'm just a little confused because your Hamiltonian density has got that integral. The last thing you wrote. And then
That's the full Hamiltonian.
Yeah, but I'm wondering why we haven't integrated over.
Oh, you're right. You're right. Yeah. Okay. Again, I must apologize. I've confused myself again. So here I was. Yeah. So. Right. So let's do it. So I'll do the bulk first. And then when it's time to write this, I'll reinsert the boundary term. That's really what I should have done. So sorry about that. So H bulk is going to be, well, I should not have erased all of this. Let's go back. So I get 2n KAB plus NA slash B plus NB slash A. That multiplies so that's H bar dot. That multiplies root H KAB minus KHAB. And then I'll subtract the bulk part of the Lagrangian, which is n root H 3r plus KAB minus k squared. All right, so I'll try to go mistake-free from here. So let me collect all the n root h terms, as I was starting to do. So we get 2 KAB minus 2k squared. So that's what I had just before. And then we have minus 3r minus KAB plus k squared. So we'll see some cancellations taking place. And then the rest of it is where I have my square root of h. I have KAB minus KHAB. And that multiplies, and here I'll do something a little bit slick. Instead of taking the symmetrized combination of NA differentiated with respect to B, I'll just pretend that this is twice NAB, and it doesn't matter because this combination here being symmetric means that after multiplying by NAB, only the symmetric combination will contribute. So I can save myself some writing and simplify the expression and compensate by a factor of 2 by just getting rid of one of those terms and just rewriting in this form. All right. So here I get partial cancellation here and here, partial cancellation here and here. And what I get for the first term is n root h KAB minus k squared minus 3r. So that's the first part of my bulk Hamiltonian. What I'll do for the second term is to transfer the derivatives because I'll want to do an integration by parts in just a few minutes. So here I have a factor of 2 square root of h. And what I'll do here is to take a full derivative of KAB minus HABK having multiplied by NA. So I'll differentiate all of this with respect to B. but then I'll compensate for this by subtracting 2 square root of h, the derivative of KAB minus KHAB with respect to B that multiplies NA. All right. So now I can integrate, and after integrating, what I can do is to finally bring the bulk term, bring the boundary term in, and the boundary term will be exactly the same one, but it will come with a minus sign now because of this minus sign over here. So after integration, I'll get disk ball term and disk ball term inside my Hamiltonian. This will become a surface integral because it's a full divergence. So we're going to use Gauss's theorem to so that's the divergence of a vector, that lives inside the bracket. So I'm going to use the divergence theorem to put that over to the boundary. And now we're going to have a clean expression for our Hamiltonian that's going to involve a bulk term and then a boundary term that will include that extra term together with the one that was there initially. And that, fortunately, is the endpoint of the calculation. So just to keep going, the full Hamiltonian, let's see how I want to write this. There's a factor of 16 pi that's inherited from the action over there, so I'll put it in. So I get rid of the time integral because that's no longer part of the story. So the full Hamiltonian will be an integration over each hypersurface, and over the hypersurface we're going to get disk ball term. So n that multiplies KAB minus k squared minus 3r, and that multiplies root h d3y. So we get disk ball term, and we get another bulk term that comes from over here that comes with a factor of 2. We have this factor of the shift vector, and then we have KAB minus KHAB differentiated with respect to B, integrated over the hypersurface. So that's the second bulk term. And then we're going to get 2 boundary terms. We're going to get this new one over here that I get by just using Gauss's theorem. So that's an integral over the boundary, and that involves what I have over here, KAB minus HABK. That multiplies by NA, and this we integrate over the surface with the appropriate surface element. And finally, we get the original boundary term that now finally reappears, and we get another boundary integral that involves n k minus k naught square root of sigma d2 theta. So that's the full Hamiltonian. And I'll just do one more thing, and then I'll write it in final form. I'll just write an expression for this. So the directed surface element, that's a 3-dimensional surface, right? We're integrating over that rim over here, the ST surface. So that can be expressed in terms of a normal vector RB that we introduced before, and that will involve also, the integration measure in the induced metric associated with ST. So with this last step, I can write down the Hamiltonian in full glory, and then I'll talk about it. So we have an integral over sigma t, so I'll just now lump the 2 boundary terms, the 2 bulk terms together. So we have the shift that multiplies KAB minus k squared minus 3r. And then we have the other boundary term that comes with the lapse. Sorry, that came with the lapse. This comes with a shift. And all of this is differentiated, so all of that is integrated over sigma t, and then we have two boundary terms. The first one involves the lapse. It involves the two-dimensional extrinsic curvature on ST. And this one involves the shift, the extrinsic curvature, the normal vector in this combination. And this is integrated over ST. So that finally is the GR Hamiltonian. And of course, it's only the gravitational part of the Hamiltonian. So this is really the gravitational Hamiltonian. If I have a matter field in my space-time, of course, I would have to do the 3+1 decomposition of its action. I would have to extract its momentum. I would have to do the Hamiltonian construction for that, and I would add it to the full Hamiltonian for the full thing. So I didn't want to go into that because the steps are, well, in fact, much easier, but they're, pretty much the same sequence of steps we did here. But in any case, we'll be happy here just to consider a vacuum theory where there's, gravity, but there's no matter. Or, we could do matter. We could just add contributions to that. It would just complicate the story a little bit, but the steps, I think, would be more or less the same as what we've seen for the gravitational part of it. It would be simpler because there was a lot of stuff that happened for the gravitational case, mostly because of and needing to keep track of the boundary terms all through the calculation. If we were doing this with matter, for most forms of matter, there would be no need for boundary terms, although for gauge field theories, it tends to be that those also come with boundary terms, and we would have to account for them as well and add them to the expressions over here. All right, so the good news now is that the hard part is over. We can stare at this and see what it tells us and extract all the juice from this, and that's going to be, I think, at least a lot more fun for me and probably for you as well. So you had a question?
I don't think you needed two multiplying the lambs. You factored it out.
Where?
The -2. -2, I think that should just be it. Bottom line.
Here? Oh, you're right. Yeah. Yeah, there's no 2 here. Yep. Thank you for that. Okay. Okay, so now that we have the Hamiltonian, we could do all sorts of things with it. I mean, one thing that is normally done with the Hamiltonian is to say, okay, well, let's write the, let's go back to the gravitational action. Let's write it in Hamiltonian form, canonical form, and let's do a variation of the action to get out the Hamilton form of the equations and do all of this and end up with a 3+1 expression for the field equations. If you're curious about this, you can read through the sections in the book where I go through all of this very systematically. But that would be even worse than what we've seen so far, so I really didn't want to do that in class. I don't think I've ever taught that. I mean, I did it once and I wrote it up, and then I decided to leave it at that. Well, it's something you can do on your own if you're interested. But the interest of doing this is that you would end up with a formulation of the field equations that would basically have the structure that the time derivative of the induced metric is given by the extrinsic curvature plus, the extra terms. And then you would generate other equations that would tell you how the extrinsic curvature itself evolves. And that would be a nice sort of canonical first order formulation for the field equations. And that is usually where, numerical relativity starts. They start with this and then they put some twists on that, try to come up with an even more convenient formulation. But the starting point is always a 3+1 decomposition of the field equations. And that's something that you can get probably most straightforwardly by doing the variation of the action after expressing the action in Hamiltonian form, you just go through the variation, and that's the outcome. The same way that in mechanics you can generate the Hamilton form of the equations of motion by going back to the action and doing the variation at the level of the Hamiltonian formulation. So that's one thing we can do, but we won't do that. The other thing that we'll do is to, well, look at the Hamiltonian and say, well, what if we evaluated the Hamiltonian for a solution to the field equations? Presumably there's some meaning associated with that Hamiltonian. There's some meaning that we can associate, for example, with the total energy of a space-time by just evaluating the Hamiltonian on a solution to the field equations. And there something really interesting happens. If we solve the field equations, we have to solve the constraint equations. And if we solve the constraint equations, we find that this is 0. And we find that this is 0 because those are the left-hand side of the constraints. The right-hand side of the constraints would involve matter terms that if we had included a matter field in our Hamiltonian description, we would have had additional terms here that would involve those matter terms. Now we don't have them because we're dealing with a vacuum theory. So in vacuum, the statement of the constraint equations is precisely that this vanishes and this vanishes. The Gauss-Cadazzi constraints, yeah. So something we talked about a little while ago. So the constraint equations in vacuum is just a statement that the 3 curvature plus minus KAB plus K squared is equal to 0, and that the derivative of the extrinsic curvature in this combination vanishes. So those are the Gauss-Cadazzi equations that can be formulated directly on the hypersurface. Those are components of the Einstein tensor that have to be satisfied on each hypersurface. That's what I mean by the constraint equations. And the main conclusion here is that if we satisfy the constraints, that is, if we satisfy the field equations in vacuum, that is, if we evaluate the Hamiltonian for a vacuum solution to the field equations, the bulk part of the Hamiltonian vanishes, and what we end up with here is a Hamiltonian that is pure surface. So the numerical value of the Hamiltonian for a solution to the vacuum field equations will come entirely from the boundary term. And that's pretty nice. That's a very nice structure. Interestingly, a way of deriving the constraints would be to consider a variation of the Hamiltonian where you also include n and the shift as things you can vary. Those are not canonical variables because we don't have n dot, or we don't have a p for n and we don't have a p for na. We don't have canonical momenta associated with these variables. So a variation of the Hamiltonian that includes variations of n and na are not something that give you the evolution equations for the canonical pair that we really are dealing with here. But if you do a variation including n and na, well, you're really treating them as Legendre multipliers, and basically you can view the constraints as arising as a consequence of a full variation of the Hamiltonian, including n and na as Legendre multipliers. I think you're going to ask me, well, what happens here? I think what happens here is that this doesn't contribute. So because of the rules of variation, you have to fix the variations to be 0 on the boundary. And so you can vary in the bulk, you cannot vary on the boundary. And that keeps this boundary term inert when you do the variations, at least for this specific purpose. So anyway, so that's just something you can think about, and you can read more about this in my treatment in the book. But the main message right now is that if we evaluate the Hamiltonian for a solution, so for a solution to the vacuum field equations, and in fact, that property would be true also for non-vacuum solutions because, for most matter fields, If you were dealing with a fluid distribution or dealing with a scalar field or something like this, the matter part of the Hamiltonian would also be bulk, and it would be additional terms within the constraints, and that property that the Hamiltonian is a pure boundary term in the case of a solution would also be preserved. So it's true for vacuum field, for solution to the vacuum field equations. It would also be true for solutions with matter, provided that you're not dealing with a gauge field theory. So if you're dealing with a gauge field theory as a source of matter, then typically you would find that there would be additional terms in the Hamiltonian in the bulk term. But I won't deal with those complications here. Anyway, for a solution to the vacuum field equations, what we find is that the Hamiltonian evaluates. So now it's the solution valued Hamiltonian after we have, found a solution where we can't vary the Hamiltonian anymore. So it's really an evaluation of the Hamiltonian for that solution. It ends up being a pure boundary term. And the main task now is to come up with an interpretation of this. What is this quantity supposed to mean physically? So I'm just rewriting what I had on the board. So this is a pure boundary term, which is, pretty interesting. But now the question is, okay, well, what do we do with that? What does it mean? Can we find a compelling way of saying that this represents the total energy of the system? And is there more to it than that? And in fact, there's quite a bit more to it than that. One thing that's interesting is that the Hamiltonian continues to depend on the lapse and shift. And the lapse and shift, as we said all along, are things that specify the foliation, and things for which, they don't specify the foliation, they specify the flow across the foliation. So I can choose a foliation, and then I can choose my flow, my flow lines to which, the vector T alpha is constant. So the lapse and the shift specify the flow once I've made the selection for my foliation. So the lapse and the shift are completely arbitrary. I can choose them in any way that I want. And presumably, to each choice that I make, there will be some different value for the Hamiltonian, and perhaps with a different meaning to it. So that's what I need to, that's what we need to think about. So how do we make meaningful choices for the lapse and shift, and how do we extract something physically meaningful about the Hamiltonian? But something that should already be clear is that we're going to get more than just one thing out of the Hamiltonian, because we have a lot of freedom in specifying what we might want for the lapse and shift, and to each choice we will get a different Hamiltonian, possibly with a different interpretation. The point is that there's a lot of information contained in this, and there's a lot going on inside the Hamiltonian that's not just about total energy. And in fact, what we're going to do here is to introduce meaningful choices for the lapse and shift that will allow us to extract things like total energy, total momentum, total angular momentum. All of those quantities that are very important for space-times are contained in this, and they just differ from each other by making different choices for the lapse and the shift. Okay, so let's talk about that. So just to summarize what I just said, so the Hamiltonian depends on the foliation, of course. So it depends on how I choose to slice my space-time, and it depends, of course, on where I pick my boundary. For the rest of the discussion, I'm going to be thinking about space-times that are asymptotically flat, And it's going to be natural to try to push this all the way to infinity and consider surfaces that basically go all the way to the asymptotic region where things go to a flat, to a flat space-time. So the Hamiltonian depends on the foliation. It depends on where I pick the boundary, but it also depends on choices that I make for the flow, as described by my lapse and shift. So this is really a choice of flow. And what I mean by flow, of course, is this congruence of curves to which t is tangent. So lots of freedom into the Hamiltonian. What I'm going to do first is to restrict the freedom in choosing the foliation so that we can make contact with asymptotic flatness. And then I'll consider what kind of choices we might make for this so that we can extract something meaningful out of the Hamiltonian. So the application that I want to consider here is to asymptotically flat spacetimes. And that's a choice. You could, choose to alter this. You could choose to do, asymptotically ADS if you wanted to. You could do asymptotically de Sitter if you wanted to. You would just need to adapt a few things, but in principle, it can all be done. So here, it's really an application to a very specific choice of asymptotics. What I'm going to do is to take this context as a way of motivating a restriction on what types of foliations I would want to have. Because if I go to so basically, I'm going to be interested in pushing this to infinity, but I want to do it in a way that makes contact with asymptotic flatness, and the fact that if I'm out at infinity and I have asymptotic flatness, I'm basically working in flat space-time. Safely out at infinity, I'm dealing with flat space-time. And I could choose to be perverse and pick a foliation that has nothing to do with surfaces of constant t in Minkowski space-time. But I don't want to be perverse. So I'll do something where my hypersurfaces here, which can be arbitrary in the bulk, will asymptotically approach a surface t equal constant in Minkowski so that I can make easy contact with asymptotic flatness. So what we're going to do here is to assume we're going to restrict sigma t such that it approaches a surface. In the notes, in the book, I called it t bar just to distinguish the original t and ya coordinates that we had in the bulk to the asymptotic coordinates which we might use at infinity. So I'll call that one t bar. So I'm going to restrict the hypersurface so that it approaches, it coincides asymptotically a surface t bar equal constant in the asymptotic Minkowski spacetime. So I'm going to have a frame t bar, x bar, y bar, z bar at infinity, and I'm going to call that the asymptotic Minkowski frame. So I'm going to pick Eilorent's frame out at infinity, and I'm going to insist that my hypersurfaces sigma t will smoothly, smoothly approach one of those t bar equal constant surfaces at infinity. And it can continue to do whatever it wants to do in the bulk, but it's just that asymptotically I'm going to align my surface so that it meshes really well with my asymptotic frame. So what that means is that, in the bulk, so I can have a space-time, a space-time diagram in terms of my arbitrary coordinates. I can have hypersurfaces that do whatever they want to do in the bulk, but out at infinity, they're going to start behaving like they should to approach those t bar equal constant surfaces. So that would be one hypersurface, that would be another hypersurface, but again, asymptotically. So this would be sigma t2, sigma t1, sigma t0. And at infinity, we would have those asymptotic t equal constant surfaces. They cannot be extended into the bulk because, those exist only in the asymptotic region where things are Minkowski. So I draw them like this, but they just don't extend beyond, the outreaches of the space-time. But what I want is for each sigma t surface to asymptotically line up, asymptotically coincide with those t-bar hypersurfaces. Complete arbitrariness in the bulk, but we make sure that they align themselves very well with the asymptotic Minkowski frame. Okay, so I do that. I impose this restriction on the foliation. And, it's some restriction, but it's pretty limited because I still retain a lot of freedom to do whatever I want to do in the bulk. The next thing I'm going to do, of course, is to, push the boundary to infinity. So ST will be pushed to infinity, which means that, well, in the end, I don't really care about all this freedom because I'm really working out there, taking a limit all the way out to infinity, where essentially there's no distinction between my original foliation and the foliation that I'm given in Minkowski spacetime when I work in terms of that frame over here. Right? So that is a restriction on the foliation that I'm going to be using, and I'm going to be taking the limit where ST goes to infinity when I do all of this. Having introduced this restriction on the foliation, I still haven't said anything about N and NA. So I retain at this stage all the freedom that I had to specify a congruence of curves through the foliation, as described by my tangent vector field T alpha. So this flow is still arbitrary. So the flow is arbitrary. The flow, of course, is determined by N and the shift. And one thing I know about my normal vector, though, so the normal to each hypersurface is going to align itself with the asymptotic frame. And that's going to be basically a vector that's going to be aligned in the time direction. So that's going to be a vector aligned in the time direction. So I can write my flow vector in terms of N, and this I can re-express in terms of dx alpha dt bar, keeping my spatial coordinates fixed. I can do that because I know that this is going to be the normal vector to t bar equal constant hypersurfaces. Right? This is a vector, well, anyway, I think it's obvious. So a vector that points in the t bar direction is going to be normal to the hypersurfaces. So I write it in this form. And then for the other guys, of course, I have dx alpha dya, keeping t bar fixed. That's what happens asymptotically. So I still have complete freedom over this, therefore complete freedom over these things. Yep. I can choose to move in any particular direction. Right? So N tells me how fast I want to move in the time direction, and A tells me how fast I want to move in the spatial directions. So if I'm out there at infinity, I can pick any direction. I can go arbitrarily fast, and that basically tells me that I can, because I can move in any direction with any speed, I have the full freedom of specifying the flow, and that's basically given by the full freedom in specifying those two things. So at this stage, I've still retained all of this, and the point is that the Hamiltonian will depend on which particular choices that I make here. So the Hamiltonian, H, at this stage, still depends on the flow through N and NA. So that freedom is still there. Okay, well, let's pick a few obvious things and see what we get from that. Okay. So I have the complete freedom, so now I'm going to just make some choices. So let's pick n equals 1 and a equals 0. If I pick n equals 1, n equals 0, and a equals 0, what that tells me is that my flow here is going to be aligned with the time direction in the asymptotic Minkowski frame. So what I do here by picking this is to consider the flow to be an asymptotic time translation. So basically, I'm killing this term. I'm making the flow aligned with the normal vector with a unit normalization. And being normal to those hypersurface means that I'm going normal to the asymptotic Minkowski frame. That is, I'm going along the t-bar direction. So I'm doing here an asymptotic time translation. What do I get from the Hamiltonian in this case? Well, going back to the expression up here, I get that in this case, the Hamiltonian, I'm going to divide through by 16 pi, so I get 1 over 8 pi. I get a minus sign, so I get minus 1 over 8 pi. I have an integral over st, but now it's understood that we're taking the limit where st goes to infinity. And we get n, which is equal to 1. We get k minus k naught. That's integrated over our 2 surface before we take the limit, where we take it to infinity. So for that choice of lapse and shift, I get this neat expression for the Hamiltonian. And that Hamiltonian is the Hamiltonian that's generated by an asymptotic time translation. That version of the Hamiltonian, because it's associated with an asymptotic time translation, we're going to call the total energy of the spacetime. That is m, the total mass, or total mass energy of the spacetime. And now we have this, I think, pretty plausible, if not compelling relationship between time translations and the total energy of the system. And the relationship is provided by the Hamiltonian, evaluated for asymptotic time translations. So that's the total mass energy of the spacetime, and it's also known as the ADM mass. ADM stands for Arnold, Deser, and Missner, who were the first pretty much to come up with a decent Hamiltonian formulation for GR, and they basically, did all of this in different notations. So that's a notation that they didn't have. So in their original paper, they have a different expression for this, but it's completely equivalent to what I have here. So what we have here is a way of extracting a mass for the total space-time. We're going to have to convince ourselves that this is a sensible definition. It's going to have to match with other notions of mass we may have. And one, quick check would be to, what if we evaluate this for Schwarzschild spacetime, for example? Do we get that the mass as calculated here comes out to be the same thing as the mass parameter in the solution? If the answer was no, well, we'd be, on a really bad, trajectory. Things would be seriously wrong. But in fact, that's exactly what happens. And I'll go through that this afternoon. But here, the guide that we get is that, well, we have a Hamiltonian that depends on the flow. If we pick the flow to be an asymptotic time translation, then it's, it seems plausible. It seems like a compelling interpretation to see that the Hamiltonian evaluated for an asymptotic time translation should inform us, should tell us something about, the quantity that's conjugate to time in Hamiltonian dynamics, which is basically the total energy. So here we have an association with the total energy and the Hamiltonian for asymptotic time translations, and that generates, a very neat, handy-to-use formula for evaluating the mass of any spacetime. We just take our boundary, calculate its extrinsic curvature, and then compare that to its extrinsic curvature. If that boundary was embedded in flat space, we integrate and we get our number, and that number represents the mass of the spacetime. So that's one thing we can extract from the Hamiltonian. But now we can play this game differently, right? So there's nothing that tells us that we have to pick the flow to be aligned with those hypersurfaces. In fact, we can do something radical. We could consider doing, Lorentz transformations of this. We could consider moving with a boost. We could consider doing all sorts of things. And we would be constructing basically the usual types of transformations that we would have in special relativity between mass and momentum, between energy and momentum. All of that can be built in by just picking different flows. I've talked about mass. I haven't talked about momentum. So how do we get a momentum out of this? How do we get a linear momentum out of this? Well, we would expect a momentum to be conjugate to not a time translation, but to a spatial translation. So if we do an asymptotic spatial translation, presumably what we would extract from the Hamiltonian would be a total momentum. So instead of aligning the flow this way, why not take the flow to be moving on each t equal constant surface along one specific direction? We can do that. There's nothing here that tells us that we have to pick a flow that's time-like. We can pick a flow that's space-like. No obstacle doing this. And for a type of flow like this, we would get linear momentum. So if we pick n equals 0, and then if we pick NA to be pointing in some specific direction, how do I want to describe that? So if I pick NA to be something that points, for example, in the direction of x bar, then what we have is an asymptotic translation along x bar, and then the Hamiltonian evaluated for this would be the momentum in that direction. So in that situation, I won't write the equation in full because I haven't introduced notation for this, and I didn't do that in the book, but that's just for illustration, that the Hamiltonian evaluated for this would basically be, the interpretation of this, because now it's associated with a spatial translation, not a time translation. The Hamiltonian would give us the total linear momentum in the x bar direction. And obviously, we can do the same in the y bar direction, the z bar direction, so we can construct essentially a linear momentum vector by combining those three numbers. And we can combine all of these things by taking flows that are boosted relative to those elementary flows and basically construct an algebra of how these things transform under Lorentz transformations. All of this neatly formulated in the asymptotic frame and so on and so forth. So the Hamiltonian gives us also a way of extracting the linear momentum of our spacetime. Typically, that doesn't play a big role in calculations because typically we always pick the rest frame of whatever lives in that space-time. So we always pick a frame that has no total linear momentum. So typically, that's a quantity that is chosen to be zero by just working in the center of mass frame of whatever lives in the space-time. So that's why I didn't focus on that in the book. But that's one of the ADM quantities that these guys introduced. And it's extracted in a very similar way from the Hamiltonian. The one more thing we can do on this is to pick an asymptotic rotation. If we pick the flow to describe a rotation, then we'll have a Hamiltonian evaluated for an asymptotic rotation, and that will give rise to an angular momentum. And that's a bit more interesting than linear momentum in this context. So if we pick n to be 0, and if we pick the lapse to be a rotational vector, so something that points in the direction of, that follows the flow of a rotation, so something that would be given in terms of dxy d phi bar a, d phi bar, so phi bar is a rotational coordinate in the asymptotic Minkowski frame. Then, so the flow describes a rotation. The flow, follows a rotation. And the Hamiltonian we extract from this is going to be an angular momentum. So here, in this case, I'm going to take the Hamiltonian up here. I'm going to put n equal to 0. I'm going to be putting phi, substituting NA for the appropriate rotational vector. And the only other thing that I'm going to do is to introduce a minus sign, which is conventional. So the Hamiltonian in this case is going to be plus 1 over 8 pi, the integral of st going to infinity. And then we get our extrinsic curvature. That's multiplied by our rotational vector and the normal vector to the hypersurface, to the two-dimensional surface. We do the integral. And that, because now we have an association with an asymptotic rotation instead of a translation, that has the interpretation of an angular momentum. And what's conventional here is to put a minus sign. So the angular momentum is going to be, by definition or by convention, minus this, and that's to be sure that we have the proper right-hand rule associated with the angular momentum vector. So this is the total. So this is the definition of J, which is the total angular momentum vector, or the total angular momentum in the direction of, well, the axis orthogonal to that rotational angle and of the rotation axis. So again, a nice and fairly plausible and compelling association between angular momentum and Hamiltonian, the same way that we had an association with total energy or total mass. All of this basically comes from the same construction, where we just specialize the flow to be in the direction that we want, and corresponding to that choice, there will be a different interpretation for the Hamiltonian. We have the interpretation for time translations. We have the interpretation for spatial translations. We can mix them up and consider Lorentz transformations between all these quantities, Or we can pick the flow to be, describing a rotation, in which case we get an association between the Hamiltonian and an angular momentum in that in the direction of the rotation axis. And then, of course, we can pick different rotation axes. We can pick different angles, and we'll pick an angular momentum, for that particular axis. And we can, combine these things and consider 3 orthogonal directions in which to do the rotation and build an angular momentum vector from all of this. So I'll come back to that this afternoon. I think it's more than time to break up. But there are really things to do here. So here I've sort of I basically just declared that those would be nice and sensible definitions for these things. But if they didn't align with other notions that we have of mass and angular momentum, if it didn't reproduce our other notions of mass and angular momentum, all of this would be very pretty but completely useless. So we have to at least verify that this is not only nice as a matter of definition, but it actually produces physically sensible results. So I'll talk about that this afternoon and give more discussion about these things. Any questions before we break? Yep.
So how does this, if we integrate the density coming from mapping the energy momentum tensor on each of the hypersurfaces?
Yep.
Which, according to the constraint equations, is equal to that expression in the Hamiltonian, the first constraint equation.
Right.
If we integrate, how does it relate that mass given from the integration of that density on each hypersurface? How does this relate to its total mass?
That's a very good question, and that's something I'll talk about this afternoon.
Okay.
But think about this. That mass depends only on what's going on at infinity.
Mm-hmm.
The mass you get by integrating the density cares about everything that happens in the bulk, including, by density, presumably you would mean, okay, let me pick an observer that's normal to the hypersurface here, and this observer will measure a mass density here. That observer, normal to the hypersurface here, will measure another, the density here, and then you'll integrate like this across the hypersurface. All of this is very detailed and makes very specific choices for observers at each point along the hypersurface.
Mm-hmm.
And the short answer is that that definition of mass would disagree with this definition of mass because there's just too many details here to account for. That definition of mass is much more robust. I'll talk about that later on. Yeah, but this is very important, so we'll talk about it. All right, so I'll see you this afternoon.